What specific problem does the Latent Flow Transformer, LFT, aim to solve in the context of large language models? And how does it specifically address the limitations of current compression techniques like pruning and knowledge distillation?
The Latent Flow Transformer, LFT, aims to address the substantial memory and compute demands of large language models, LLMs, by providing a more efficient architecture for language modeling. Current compression techniques, such as pruning and knowledge distillation, often fail to achieve the necessary scale of reduction due to the overparameterization of many layers and the discrete nature of language, which resists continuous approximation. The LFT specifically tackles these limitations by replacing a contiguous block of transformer layers with a single learned transport operator trained via flow matching, thereby enhancing parameter efficiency. Additionally, it introduces the recoupling ratio to identify which layers are most suitable for replacement, focusing on the compressibility of middle layers, and employs the flow walking algorithm to navigate local ambiguities in latent transport, significantly improving performance. This innovative approach allows the LFT to compress multiple layers while maintaining lower performance degradation compared to traditional methods, effectively bridging the gap between autoregressive and flow-based modeling paradigms.
Can you explain how the proposed Latent Flow Transformer, LFT, works? Illustrate its methodology step by step, including the role of the learned transport operator and how it interacts with the layers of the transformer.
The Latent Flow Transformer, LFT, operates by replacing a contiguous block of transformer layers with a single learned transport operator, referred to as the latent flow layer, which is trained using flow matching principles. The methodology begins with the selection of layers for replacement, guided by the recoupling ratio, an optimal transport-based metric that predicts the quality of flow matching and identifies middle layers as particularly compressible. The learned transport operator maps the input latent from the first layer of the block to the output latent of the last layer over a desired trajectory, effectively unrolling the latent flow layer into a static processing graph during inference. This operator is trained to navigate and resolve ambiguities in the latent space using the flow walking FW algorithm, which employs numerical integration to learn non-crossing trajectories, thereby enhancing transport alignment. Ultimately, the LFT achieves significant parameter reduction while maintaining performance, as demonstrated by lower KL divergence metrics compared to traditional layer skipping methods.
Provide a simple yet illustrative example of how the flow walking FW algorithm functions within the training of the LFT. Walk through a hypothetical scenario to demonstrate its effectiveness in navigating latent transport paths.
The flow walking FW algorithm operates by approximating the transport of latent states from an initial position to a target position using numerical integration across discrete time points. For instance, consider a scenario where we need to transport a latent state from layer 6 to layer 12 in the Latent Flow Transformer, LFT. The FW algorithm would define a series of discrete steps, where at each step, it slightly adjusts the trajectory to avoid crossing paths that could lead to flow misalignment. By learning non-crossing trajectories, FW effectively separates the paths around intersecting points, ensuring that the latent states are accurately transported without averaging conflicting velocity signals. This method allows the LFT to maintain a clear mapping between input and output latents, significantly improving the alignment and performance of the model compared to standard flow matching, which struggles with closely clustered trajectories. Thus, FW enhances the learning of the latent transport operator, enabling the LFT to achieve better performance with fewer layers while preserving the integrity of the original input-output relationships.
What are the key theoretical or practical advantages of using the LFT over traditional transformer architectures, and how does the implementation of the recoupling ratio enhance its performance?
The Latent Flow Transformer, LFT, offers significant theoretical and practical advantages over traditional transformer architectures by enhancing parameter efficiency and enabling simulation-free training through the use of a learned transport operator that replaces multiple transformer layers. This design allows for a substantial reduction in model size while maintaining performance, as demonstrated by the ability to compress 12 out of 24 layers into a single transport layer with minimal performance degradation. The implementation of the recoupling ratio serves as a critical tool for layer selection, accurately predicting the quality of flow matching by quantifying the alignment of latent pairings, which helps to identify the most compressible middle layers. This targeted approach not only mitigates flow crossing issues, but also ensures that the LFT can effectively learn the latent transport mappings necessary for high-quality language modeling. Overall, the combination of these innovations allows the LFT to bridge the gap between autoregressive and flow-based modeling paradigms, achieving improved performance metrics such as lower KL divergence compared to traditional methods.
Describe the experimental validation process used to test the LFT. What specific datasets and metrics were utilized, and how do these results compare with baseline methods?
The experimental validation of the Latent Flow Transformer, LFT, was conducted using the Pythia 410M model, with training performed on 2.6 billion tokens from the PILE dataset. The evaluation metrics included normalized mean squared error, NMSE, KL divergence between the LFT output and the teacher distribution, and perplexity based on the LFT's output logits. The results demonstrated that both LFT trained via standard flow matching, LFT-SFM, and flow walking, LFT-FW, significantly outperformed the baseline method of layer skipping, with LFT-FW achieving performance parity with a regression model that utilized a single transformer layer. Notably, LFT-FW consistently outperformed both baselines in terms of latent state matching and downstream language modeling, indicating its effectiveness in learning latent transport trajectories. The experiments highlighted the importance of layer selection and the advantages of using flow-based training methods over traditional approaches.
Discuss the limitations encountered with the LFT, particularly regarding flow path proximity and the velocity ambiguity issues. What steps could potentially be taken to overcome these challenges in future research?
The Latent Flow Transformer, LFT, encounters significant limitations related to flow path proximity and velocity ambiguity. Specifically, as flow paths become closer together in the latent space, the model experiences a performance plateau due to the ambiguity in determining the correct velocity for transport, which is a known challenge in flow matching models. To address these issues, the proposed flow walking FW algorithm enhances the learning of latent transport by exploring paths with a clearer view to the target, effectively navigating local ambiguities and improving transport alignment. Future research could focus on refining the FW algorithm further, or developing alternative methods that enhance the stability of velocity field estimates, potentially incorporating additional regularization techniques to mitigate the effects of intersecting trajectories. Additionally, investigating more sophisticated velocity field learning strategies could help in overcoming the inherent challenges posed by flow path proximity.